Hi everybody, I'm Mehdi. First of all, I like to apologize for not being able to attend the conference and the workshop for some reasons. And second, I would like to thank the committee for letting us to present this work offline and remotely. So today I'm gonna talk about the controlling of the traffic lights by means of multi-agent systems, action theory, and machine learning techniques. Uh, as you might expect, the traffic signals are the biggest impediment for the efficient operation of the surface arterials. There are already uh, algorithms for optimizing the signal timing plans like transit, which is an offline optimization algorithm. Uh, Also, we have traffic responsive controllers like Scoot and SCATs. Uh, However, there are difficulty adjusting to changing in traffic patterns. Also, they are using centralized approach. Examples of decentralized uh, uh, adaptive systems are Protein, OPEC, Utopia. However, they have complex computation and communication schemes, so it makes the implementation difficult. Uh, so more flexible and robust approaches are necessary for optimizing and controlling traffic signals. As you know, multi-agent systems have become a promising application domain within artificial intelligence for optimizing traffic signal control. They provide good paradigms for systems which are distributed, stochastics, dynamics, and heterogeneous. And all of these characteristics, you can see all these characteristics in modeling traffic signals. This paper shows how the traffic interaction of intersection can be regulated by action theory, multi-agent system, and machine learning techniques. There are two sets of related work to what we have done in this paper. One set of works are those who have used multi-agent systems and reinforcement learning. Example of this set of papers are like the paper that was presented by Choi and his colleagues. They proposed a hierarchical multi-agent system that consists of 3 layers of agents: controller agents, zone controller agents, and regional controller agents, in which each agent handles a different part of the system. Another example is the work done by Tantawi and her colleagues. They proposed a multi-agent system approach for adaptive traffic signals, in which each agent, which controls one intersection, plays a game with its immediate neighbors and learns and converge to a response policy to all neighbors' policies using a reinforcement learning techniques. The other sets of related works are those who have used the market-based ideas to traffic signal control. One example is the work done by Dr. List and his former PhD students. They demonstrated that the action theory can be used as a paradigm for modeling signal control. The other example is the work done by Vazirani and his colleague. They demonstrated that a distributed market-inspired mechanism can be developed for the management of an urban road network where drivers trade with the infrastructure agents in a virtual marketplace. So basically, it's a vehicle to infrastructure communication kind of thought, and vehicles, which are agents, they reserve and buy a trajectory to pass the intersection. So, inspired by the work done by Dr. Liss and his former PhD students, we are also using a market-inspired approach. Uh, we are viewing the intersection as a commodity whose temporal, non-overlapping usage can be adjudicated through an interactive bidding process that involves multiple agents. Each movement, as you can see in this intersection, each movement is controlled by an agent, and also we have an intersection agent. So we have movement manager and we have intersection managers. In a typical intersection, if we consider true and right as together, we have, and left separately, we have 8 movement manager and 1 intersection manager. So bids occur each time the use of the intersection is contested. This arises when agents for conflicting movements have non-zero queues and transitioning to a new stage is possible. So stages or phases are formed by combinations of winning bidders. 8 stages or movement combinations are possible for the intersection shown in figure. So on the left-hand side corner of the figure, there's a table that shows the movements and the combination of movements. And we have 8 stages which are formed by the combination of movements. For example, stage 0 is a combination of movements 0 and 4, and so on and so forth. Movement managers receive tokens when the vehicles join their queues. They receive tokens or fee or whatever currency you want to interpret. We call them token. So 1 token per vehicle, they pay that to the movement managers, and movement manager use that token to pay the intersection manager when they win bids. The bidding process is as follows. Each movement manager with a non-zero queue submits a bid, and intersection manager sums these bids for all possible safe movement combination. As I said, we have 8 possible safe movement combination. For example, if movement managers bids like 1, 6, 2, 5, 3, 2, 4, 5 for respectively for movement 0 to 7, the combined bids would be 4, 3, and so on and so forth. And in this example, you see that movement 2 and 3 and 7 have the highest bid, so they get to use the intersection, and they pay the intersection manager what was the bid, which was 10 token, and it's a first price bidding auction. So they pay 10 tokens and they get to use the intersection. So the movement managers have access to information about their respective movements, and they have limited information about the other movement managers. They know how many drivers are in queue, how many tokens they have, the bid they have submitted, and what was the winning bid. When movement managers win the auction, they get to use the intersection for a minimum green. And when the minimum green expires, they have to bid again to retain the control for the intersection. So here in our scenario, if the movement managers currently holding control of the intersection submit winning bids, the green will be extended for them. Here we are assuming that the extension is 3 seconds. If a different combination of movements win the auction, the traffic lights goes under a change interval of 4 seconds. As you know, the typical practice is that we have yellow and all red. That's the change interval we are talking about here, which we are assuming that it's 4 seconds. So if we have a different combination of movements, the whole traffic lights goes under this change interval. Reinforcement learning has been used to help The movement managers improve their bidding strategy based only on the knowledge of their own past experience. As you all know, Q-learning algorithm, the core of the Q-learning algorithm is a table which stores the value of each state and action, and we have an update value for each state and action. In our scenario, state is the current queue in each approach, action is the bid amount submitted, and reward is the difference between the total cumulative delays of two successive decision points. If the reward has a positive value, this means that the delay is reduced by this value after executing the action. Movement manager use an epsilon greedy selection approach in order to explore the state action environment. As you all, I'm sure you know, initially it makes sense to do more exploration and then more exploitation. So we have used the exponential function. Initially we have more exploration, and as the number of iteration increases, the exploration decreases as well. The learning rate, we have used this equation where the denominator is a constant. We have used 0.2, and the denominator is the number of visits to a particular state action pair. This slide shows the overall pseudocode for the simulation. We have a set of inputs. We have a minimum green of 6 seconds, change interval of 4 seconds, which is a combination of yellow and all red interval. We have a saturation headway of 2 seconds, and initial fee for each vehicle is considered 1 token. Initially, each movement managers initialize Q values as 0. For each time step, each movement manager collect fees from the arrivals, and they add new arrivals to service queue. If the use of the intersection is contested, each movement managers who submitted bid in previous bidding cycle, they compute their reward and they update their queue value. And those who have non-zero queues participate in the auction again. As I said before, we are using an epsilon greedy. Movement managers submit bids randomly with probability epsilon, and they submit according to policy with probability 1 minus epsilon. In the first case, when they submit randomly, the bid is subjected to a minimum of 0.5, and the maximum is subjected in a way that the total bank balance is equally distributed among all vehicles in queue. So movement manager submit bids, intersection manager sums submitted bids for all possible safe movement combination. The pair of movement with the highest combined bid will be selected, and they pay the intersection manager what was the bid, the first price bidding. And as I said before, if the current winner is the same as the previous winner, intersection manager extend green by 3 seconds. Otherwise, the traffic lights goes under a change interval of 4 seconds, which is a combination of yellow and all red, and then the intersection manager allocate intersection control to new winners for the minimum green. Figure below shows, this figure shows the network of intersection which has been modeled. So each intersection implements the proposed control strategy separately. We have 4 intersections on the east-west arterial and 3 on the north-south arterial. In the figure, you can see the distance between intersections. 2 different combinations of traffic volumes shown below are considered in this study. The first one, the case 1, represents a low volume of traffic, and case 2 represents a high volume of traffic. Traffic increased by 25% in the second case. So for example, for intersection 0, we have 200 vehicles per hour for north and southbound, and 600 for the eastbound. So three control strategies are explored. Other than the proposed control strategy, we have 2 other control strategies, including pre-time and fully actuated, for comparison with the proposed control strategy. Uh, all three of control strategies have been implemented in the custom built traffic simulator developed by us. We have chosen to use a custom built traffic simulator since we are using this traffic simulator for other research purposes, so we have used it for this paper as well. For the pre-time control strategy, Synchro 7, which is an analysis and optimization program, we have used Synchro 7 to come up with the optimum signal timing plan. So we gave the inputs to Synchro 7, and whatever we got from the Synchro 7, we implemented that signal timing in the traffic simulator. For fully actuated controller strategy, the implemented logic is as follow. We have sensors in each directions, and normal stage rotation is followed from a stage 0 to a stage 7. And in the absence of any request for service in the side street, the controller gives the green to the main street phase. Also, we have minimum gain of 6 seconds and maximum gain of 40 seconds for this logic. In this slide, you see the results of the simulation for 2 traffic volume cases. In both cases, as you see, the proposed control strategy improves as the time passes. And in case 1, which is a low traffic volume, it is performing better than the other 2, and pre-time is performing the worst. It makes sense because when we have low traffic volume, it's not good things to impose a predefined timing plan. So that's why the pre-time is not performing good. In the second case, the proposed controller strategy is performing in the middle, and pre-time is better. Again, it makes sense for heavy traffic. Usually, it's a good thing to have a predefined timing plan, and usually it's the case that for heavy traffic, pre-time controller strategies performs better. So that's pretty much all that I wanted to talk about. In this slide, you see the future work suggestion. In this paper, we have used the epsilon greedy algorithm. There are other algorithms that we can use for exploring the state action environment, like epsilon softmax and softmax. The other area of research is to use second price bidding. As you know, in the second price bidding, the truthful bidding is the dominant strategy. So it makes it attractive to use the second price bidding and see how it changes the results. Right now, the intersection managers are not cooperative. So the other area of future research is to make intersection managers cooperative and see how it affects the performance of the whole network. And last but not the least is the linkage of the developed signal control to a commercially available traffic simulator like vSim or Paramix. As you know, these traffic simulators have modules that we can implement the control logic within that module and connect that control logic to the traffic simulator, so we can compare the performance of the control logic in real world cases. And also they have in vSim and Paramix they have other control strategies like Scoot and Scats, so it's a good way to compare the results in a real world scenarios and also compare the controller strategy with other controllers. Thank you all. I hope I haven't bored you with this presentation. I hope you enjoy the workshop and conference, and bye bye.